So what are we going to do next is to take our affiliation graph model and simplify it into something that we will call BIGCLAM, which will allow us to detect communities in large networks. So let's see how we do this. So the previous case, what was kind of problematic in terms of trying to fit the model to the data is that we had this big, bulky, bipartite structure that we had to fit and basically search over this affiliation graph. So what we will do now is basically relax the model a bit. And the idea now is to say, rather than for every node to have 0-1 type of membership, in a sense that I can either be a member of a given community or a non-member, now we want to actually model the strengths of every node community membership. So the idea will be that we will have this non-negative strength of every node being a member of a given community. Of course, if a strength of membership is 0, this means a node is not member of the community, and if the strength of a membership is very high, this means that the node is very kind of active part or an active member of a given community. The way we will think of these strengths, we will label them as F, U, A, where U is the name of the node and A is the name of the community. So we will call this membership strengths F. And they are non-negative values. So basically 0 means no membership, and anything greater than 0 means that you are a member of a given community to a given degree. So now the question is, how do we think about links of the network arise from this model? And the way we will think about this is very similar to what we have been doing so far. So we will say that each community A links nodes independently, and the probability that two nodes are linked due to a given community, meaning them being a member of a given community, is simply 1 minus the exponential of minus product of the membership strengths of the two nodes in that given community. So the idea is very simple, right? If we are both members to that community to a very high degree, then a product will be large. We have a minus sign here, so exponential of a very large negative number is something very small, so the total probability will be high. For example, what is also a nice property of the product is if node V is, for example, not a member of a given community and node U is a member of that community, then it will be 0 times something else, so the whole thing will be 0. That is also nice. And then another thing is, if we have nodes that are members to a given community to varying degrees, we will take the product of the two corresponding strengths to compute the overall linking probability. So now this is the idea of having a linking probability for nodes U and V belonging to a single community A. So now what happens if nodes share multiple communities? In order to achieve this, we have to first define what we will call the community membership strength matrix F. So here is my matrix F, and let me tell you what its structure is. So this matrix F has the number of columns, which is the number of communities in our network. And the number of rows of this matrix equals to the number of nodes of the network. And every entry of this matrix tells us to what degree does a given node in a given row X belong to a given community in a given column. Okay? So what we can then do is, if we think of a single row basically being a description of what are the communities a given node is member of, and to what strength is a given node the member of that community, we can basically think that this completely specifies the community structure of our network, right? For every node, we know what communities it belongs to. And we can think now of every row in this case as a simple vector of community membership strengths for that node. So as we have discussed, now the question is, how do we compute the probability of a connection? The way we compute the probability of a connection is simply probability that is proportional to the product of the strengths of the two nodes. So we have already seen the equation. It is simply probability of a pair of nodes being connected due to a given community A to be 1 minus the exponential of minus the product of the strengths of the community membership of nodes U and V to a given community A. So now that we know how likely is a pair of nodes being connected due to a membership to a given community A, now we want to generalize this and say, what if a pair of nodes has multiple communities in common? And we will use the same approach as we did with the affiliation graph model. We'll say the probability of a pair of nodes being connected is proportional to the idea that at least one of the communities they have in common created an edge. So here it is. The probability of pair of nodes being connected is simply 1 minus the product over the communities, 1 minus the probability of them being connected given that they share a membership in a given community. So this formula simply says what's the probability that at least one of the communities creates a connection. So what we want to do now is think about this formula a bit more and actually try to simplify it. So let me show you how we can simplify it further. What we have so far is to say, given community A, here is the probability that a pair of nodes is connected due to the membership to that community. Then we said, right, that probability of nodes being connected in the network is proportional to the probability that at least one common community that they have that a pair of nodes has in common links that given pair. So I have the expression from the previous slide. Now let's try to simplify things a bit, right? So the first thing I can do when I have this value p sub c, I go and insert our expression for the probability of an edge. And now what I notice is that the first one and the second one will cancel out. So all I will be left with is a product over the exponentials and then a product of the membership strengths. A product of the exponentials is sum of the things in the exponent. So I can simplify this simply to say this is 1 minus exponential function and then a sum over the communities, product of the corresponding strengths, and then I have this minus here. Now what we notice is that the summation that we have here is simply a dot product, right? We are going and multiplying the components of the two membership strengths vectors together. So to write this more compactly, here's the expression. We say that probability of node U linking to node V is simply 1 minus the exponential of minus, and then it's a dot product of factor, or basically a row for node U and a row for node V, right? Where these rows basically tell us to what degree is a given node member of a given community. So to give you an example, here I can think of my matrix F, where I have the factor vectors, the community strength membership vectors for the 3 nodes. So now I can start asking, what is the probability of a given pair of nodes being connected? So for example, I can compute, given the formula above, the probability of nodes U and V being connected. That is very simple. It is 1 minus the e raised to the power of minus 0.16. If I do that, the value is 0.14. So this is for nodes U and V being connected here. What we see is that they have, the only reason they can be connected is because they share the membership to the 4th community. I can, for example, ask what is the probability of nodes U and W being connected. Here is node U, here is node W. What we notice is that they have one community in common, the same as in first case, but now they both are have very strong membership to that community. So the overall linking probability that we compute out of this is very high. But for example, nodes V and W have the linking probability of 0. Why is that? Is because V and W have no common communities, right? In the first case, one is a member of the first community and the second node is not, and so on and so forth, right? So what do we see from this is that kind of the model has exactly the components we would like. If nodes are members to a given community with very high strength, the probability is large. If the strength is low, the linking probability is correspondingly smaller.